Okay, hi everyone. Part A. Find the formula for the linearization of the function f of p equals 2 cos p sine p at the point p equals pi over 4. Okay, so first I'm just going to rewrite my function because I don't like this notation as much. I like this notation. It's almost the same, but I map a real number to the plane. And actually this will give an ellipse. And so at the point pi over 4, that gets mapped to root 2 over 2 times 2, and then root 2 over 2. Okay? And now what's the linearization? Well, it's the linear approximation. It's just another word for it. And so we need the derivative. So first I'll look at the Jacobian. Jacobian has one column for d by dp, derivative with respect to p. So the Jacobian is negative 2 sine p and cos p. Has one column. Okay. At p equals pi over 4, cos and sine are root 2 over 2. Root 2 over 2 times 2 will be, and then I have a root 2 over 2 down here. So there's a Jacobian at a point. You see it's an actual vector. It's pointing somewhere in two-dimensional space. Well, I guess it's pointing like that because the first component is negative. So it looks like that. Okay, now, so the derivative of, well, let's call this f of f at pi over 4 is the linear map. It has the same inputs and outputs. And so I'll just call the real number, I'll call it v1. And it gets sent to v1 times this particular vector that's pointing somewhere. So all multiples of that vector are the outputs of the derivative. Okay, so the derivative is that linear map. And so the linearization, at the point pi over 4 is f of pi over 4 plus some little change is basically f of pi over 4, except we're going to change it by a linear amount, namely the derivative of f at pi over 4 in the direction v, where we changed. Now, of course, because our input space is the real line, our v is really just a number, like how far we move right or left. That's our v. But here is the linearization. So this is I guess part A. Part B, use the linearization to approximate the value f of pi over 4 plus 0.1. So if you forget that linearization is just linear approximation, just another word for it, you could look at part B and see that, oh, I bet this is linear approximation formula. And this is an important skill in math, is to be able to try to figure out what people's words mean. Okay, so now we're going to take point 1. So f of pi over 4 plus 0.1, our input space is the real line, so we're just moving a very small amount to the right. Well, that's f of pi over 4. Pi over 4 goes to this vector, so I'm going to write it as a column. That point plus the derivative when I plug in 0.1 times this. Okay, so this is our approximation for this output. It won't be exactly correct. Who knows how to write down root 2, I guess 1.41 something. But I could just show that I know how to linear combine vectors. And then the second component is root 2 over 2 plus 0.1 times root 2 over 2. But either way, this is our approximation, so that's part B. You could leave it as that, or you could write it as that. Now part C, draw a picture of the situation. And then if you want, you can go to our Canvas website and click on the GeoGebra program to visualize this. But what we have here is a parameterization of an ellipse as the image of this map inside of the output space. And that ellipse will look something like this. And our point is somewhere. This is our point, and then we're going to have sort of, in our mind, we think of that, and this is our approximation here. And the true value was like maybe here. Who knows where the true value is? It's definitely on the ellipse. So I'm going to zoom in. Zoom in. And here I have the ellipse. Here I have f of pi over 4. Here I have the actual value, f of pi over 4 plus 0.1. And here I will have our linear approximation, which is, this thing here. Okay? It's basically correct, but not quite. Okay, that's it. So in order to do the linearization, you have to compute the derivative. So that's a linear map. Here's the map. And then you need to shift it by the output at the original point, right? So you have to compute the derivative at a point in order to get a linear map. And we do that by taking the Jacobian and plugging in, and then taking a linear combination. Then here's this formula for linear approximation, also called linearization of the function. And here's the picture of what's really going on. We're trying to estimate this thing by just moving in a linear way from our original output.